So today I plan to talk to you about and show you how and why the derivative of e to the power of x is indeed itself. I'll show you a bit about how the derivative of e to the power x is equal to e to the power x, and then we'll take it a step further and see how the derivative of e to the power of kx is k times e to the power of kx. So I think to start with, it's important to know what e to the power of x is and how it's defined. E is actually a secret function taking its power as an input. It's called exp, where exp of x is the sum to infinity of x to the power r divided by r factorial, starting at r is 0, which, writing out a few terms, comes out like this: 1 plus x squared over 2 plus x cubed over 6 plus x to the power 4 over 24, going on forever. To show you how accurate the sum is, let's input x as 1 into the first 5 terms and see how it comes out. You can see we get a result of e being about equal to 2.71 to 3 significant figures, where the actual value is 2.71828 and so on. The factorial, by the way, if you don't know what it means, is just the product of all the integers from 1 to that number. So 3 factorial being 1 times 2 times 3 equaling 6. So when we have this sequence, we can then take the derivative of e to the power x. And to do that, we simply apply the power and addition rules to the right side. So we take the derivative of 1, which just cancels out to 0. Then the derivative of x is just 1. After that, the derivative of x squared comes down to 2x, x cubed to 3x squared, and x to the power 4 to 4x cubed. And as a general term in this sequence, x to the power of r becomes r times x to the power of r minus 1. At this stage, it's also helpful to write out our denominators, the factorials, a long way, so that it's easier to see how it simplifies later. Now, simplifying our fractions down, you can see that our coefficient on the x term on top is continuously simplifying with the largest number on the bottom. We can see that the 2x divided by 1 times 2 simplifies to x over 1, and so just x. Then 3x squared divided by 1 times 2 times 3 can simplify to x squared over 1 times 2, and so on. But the important one in our proof, the general r times x to the power of r minus 1, divided by 1 times 2 times everything up to multiplying by r, simplifies to x to the power of r minus 1 divided by 1 times 2 times everything up to r minus 1. It's r minus 1 because of the factorial. The previous number in that product will be r minus 1. You might want to just pause for a second and make sure that that makes sense for you. We can now clearly see that this derivative is almost exactly the same as our exp function. The only difference is our general term, which is now x to the power of r minus 1 divided by r minus 1 factorial. But this still proves that our derivative is equal to e to the power x. Why? Because remember, it's an infinite sum, and therefore there will be some r plus 1th term that when we take the derivative of it, it will cancel down to equal our rth term. The powers will just keep cascading down, and therefore the derivative of e to the power of x is simply e to the power x. Now we'll move on and take things a little further and try to prove how the derivative of e to the power of kx is equal to ke to the power of kx. So remember our little exp function. Let's input kx into it to start with, and it comes out like this. Next, we'll expand our brackets and write out our factorials in full. Now, just like before, we'll take the derivative of this sum with respect to x by just applying the product and addition rules. We can see almost the exact same pattern emerges from before. 0 plus 1k x to the power 0 plus 2k squared times x divided by 1 times 2, and so on, until our most important general term r times k times x to the power of r minus 1 over 1 times 2, and timesing everything up to r. Here we can simplify once again, where our formula comes down to k plus k squared x plus k cubed x squared divided by 1 times 2 plus k to the power 4 times x cubed divided by 1 times 2 times 3. And our rth term comes to k to the power of r times x to the power of r minus 1 divided by 1 times 2 timesing everything up to r minus 1. Now our proof is nearly ready. Maybe pause and see if you can see what we're going to do next. So you may have noticed that we can factor out k from all our terms in our infinite sum, which will in turn reduce all the powers of k terms by 1. So now we have the derivative equaling k multiplied by an infinite sum. That infinite sum of which you can see is equal to e to the power of kx. And so it is proved. The derivative of e to the power of kx is equal to k times e to the power of kx. I think that these results are really quite interesting, as we could graph y equals e to the power of x and find the gradient at many points using tangent lines. And so if you were to graph the gradient at each x coordinate, the graph you get is actually exactly the same as the original, which is really quite fascinating. However, that is everything for today, so I'll see you guys later.